Isaac Newton is famously known for many things: his laws on gravitation, his creation of calculus, and even his work on optics, which we covered in our rainbows video. Today, however, we're going to look at his laws of motion. The 3 laws of motion were created by everyone's favourite physicist, Sir Isaac Newton. He came up with a book called, and I'm gonna butcher the pronunciation of it, but he came up with a book called Philosophiae Naturalis. I forgot the name of it. What's it called? Philosophiae Naturalis Principia Mathematica, often referred to as simply Principia. This book was released in 1687, so a very long time ago. And in this book, he outlined the 3 laws of motion. So Isaac Newton's first law of motion says that objects at motion will stay at motion, and objects at rest will stay at rest unless acted upon by an external force. So these are defined within the law as being in relation to the object's immediate surroundings. So, for example, if you're sat on a plane, you're obviously moving very fast because you're in a plane, but you yourself are sat stationary. So the laws of motion for you and your immediate surroundings are you're at rest. But if you get up and start moving through the plane, then you're now at motion. However, if you were to look at just the plane would be at motion throughout and not at rest. One other thing we need to know is that true rest doesn't actually exist. Now, you're probably sat at home, either at your desk watching this video, you might be lying in bed, you might be sat on your couch. It's quite unlikely you're moving right now, so you're probably at rest with regards to your immediate surroundings. However, you're sat on a planet that is spinning around its axis, orbiting around a sun at about 67,000 kilometers an hour, which in turn is flying through a galaxy, which in turn is flying through a massive universe. So we are never physically at rest, and therefore it is important to consider you being at rest in relation to your immediate surroundings. So the definition then of an object in motion is something that is changing in position in relation to its surroundings, again relating it to its immediate surroundings. Let's consider a box on the floor, not a moving relative to its surroundings, it is at rest. And there are forces acting all around the box. We're not going to look at those for the time being though, but these forces are balanced so the box isn't moving. Now let's assume an unbalanced external force, let's say the wind, pushes on the box. This is now going to cause the box, because it's unbalanced, going to force the box to move, and therefore the object will begin to move. So it will leave its state of rest and will start to move. So objects at rest will stay at rest unless acted upon by an external force. The external force in this case is the wind, causing the box to move, and it will then leave its state of rest. Okay, Isaac Newton has another law, so the second law of motion. This law is described in a mathematical formula. Now don't worry too much about the mathematical formula, we're just going to have a play around with it for a little bit. So it states F is equal to ma. So the force is equal to the mass of the object multiplied by its acceleration. So this means that the larger the object is, the more force required to accelerate it. So we're going to look a little bit closer at mass. Now, mass and weight are often confused, and that's fine, but in physics, they're very, very different properties. Now, mass is the amount of matter that makes up something, the amount of stuff that makes up an object. So everybody has a specific amount of mass, or the amount of stuff that makes them up, and that is measured in kilograms. Now weight, on the other hand, is slightly different. Weight is related to the amount of force, or the amount of gravitational force that is acting on the object. So if you were on a different planet, your weight would be different, but your mass would be the same. Okay, now that's a very key concept. So we're going to actually look at that a little bit. So let's look at how much you might weigh, or how much somebody might weigh on the moon, let's say. Now, if we take Fred, let's consider Fred. Fred has a mass of 50 kilograms. Now, to calculate the amount of force that Fred has on Earth, or the amount of weight that Fred has on Earth, we need to multiply that by the acceleration due to gravity on Earth. Now this is nicknamed g, and it is about 9.81 meters per second squared. So let's take our 50 kilograms and multiply that by our 9.81 meters per second squared, and this will give us our weight, so Fred's weight. So this equates to around 490 newtons. Now this doesn't really make any sense to a lot of people because nobody uses newtons as a measure of weight. We can use another unit of force in this case, so not using the unit which is the standard unit, we're going to use a unit that isn't standard. This is called the kilogram force. Now this kilogram force is the amount of force exerted on a 1 kilogram mass under the influence of Earth's gravity. So to convert between the two, you just need to divide by 9.81 or Earth's gravity. So in the case of Fred, who has a mass of 50 kilograms and a weight of 490 newtons, in kilogram force, their weight will be 50 kilogram force. So if we put Fred on the moon, the force of gravity is going to be a lot smaller on the moon. So we take his mass again, which is 50 kilograms, and we would multiply that by the force of gravity on the moon. So the acceleration due to gravity on the moon is about 1.62 meters per second squared. So if we take our 50 kilogram mass and multiply that by 1.62 meters per second squared, we will get Fred's weight on the moon, which equals 81 or around 81 newtons. Then we can convert this to kilogram force. Now again, this relates it to the amount of gravity on Earth. So if we get our Newton value, which is 81 newtons, and divide that by 9.81, we can see that on the moon, Fred would weigh around 8 kilogram force. It is, however, very important to remember that Fred's mass is 50 kilograms wherever he is. He's not going to gain any stuff or any matter. He's just going to have differences or different gravitational forces of attraction acting on him, which causes his weight to change. So that's the difference. Weight is related to gravity and the gravitational force, and mass is the amount of stuff that makes you up. If you want to work out your weight on the moon, you can either follow along with what I've just done there, or if you head over to the website that I'll link in my bio, it will work out your weight on all of the planets that are in the solar system. So that would be pretty cool. And finally, Isaac Newton has a third law. Now this law states that every action has an equal and opposite reaction. So if we take our example of the box again, the box is on the floor, it's got forces acting all around it, the force of gravity pulling it to the floor. Now the fact that that's happening must mean that there's something pushing up from the ground which is equal and opposite to the force of gravity. Think of this as the Earth is pulling on the box and the box is pulling on the Earth, which is what I think a lot of people say when they describe this law. If we take this further though, let's say we put the box on a skateboard and Fred comes in on a skateboard as well. If Fred were to push on the box, they would cause the box to move. The box would also, however, push back on Fred with an equal and opposite force, which would mean that Fred would also start to move. The distance they travel may not be the same, however. Now this is due to the second law of motion. If Fred were to have a larger mass than that of the box, then Fred's acceleration would be lower in order to keep the force constant. As such, the distance travelled would be different. As always, if you've enjoyed this video, please leave a like, a comment, and even consider subscribing. I'll be making more science and tech videos like this every other Saturday on the channel, so keep your eyes peeled for that. But for now, I'll see you in the next one.